Hello there, and welcome. Tonight I want to take you somewhere special, somewhere beyond the familiar glow of the planets you might have learned about in school, beyond Mars with its rusty deserts, beyond Jupiter with its swirling storms, beyond even Neptune, that beautiful blue giant marking what we once thought was the edge of our planetary family. Tonight, we're going to drift together into the mysterious outer reaches of our solar system, into a realm where darkness reigns supreme and where something extraordinary might be hiding, waiting patiently for us to discover it. It's a journey that begins not with certainty, but with a question that has been whispering through the halls of observatories and the minds of astronomers for years now, growing louder with each passing season of observation and calculation. You see, there's something peculiar happening out there in the cold depths of space, something that doesn't quite add up when we look at the mathematics of orbital mechanics and the strange dance of distant icy bodies. It's a mystery that might seem like pure fantasy at first, the kind of thing you'd expect to find in science fiction rather than serious scientific journals. But the evidence keeps mounting. The calculations keep pointing to the same remarkable possibility. What if there's a ninth planet in our solar system, a world perhaps 5 to 10 times more massive than Earth, slowly circling our sun in the outer darkness? And here's where our journey takes an even more intriguing turn. What if this Planet 9, this hidden giant, isn't as far away as astronomers initially calculated? What if it's actually much closer than we think? Perhaps close enough that we've been looking right past it, searching in all the wrong places while it drifts through a region of space we haven't properly examined. Before we continue, I'd like to invite you to make yourself comfortable. Perhaps adjust your pillow, pull your blanket up a little closer, and let your breathing slow down just a bit. This isn't a story that requires urgency or tension. There's no need to worry about missing important details if your mind begins to wander or if you find yourself drifting towards sleep. In fact, that gentle drifting is exactly what we're aiming for tonight. A peaceful exploration of cosmic mysteries where the journey matters far more than any destination we might reach. And speaking of journeys, if you're finding this exploration as fascinating as I hope you will, please consider subscribing to hear more of these cosmic contemplations, these gentle wanderings through the mysteries of space that surround us every night, hidden just beyond the veil of Earth's atmosphere. Together we'll embark on a contemplative voyage through the evidence and possibilities, through the mathematics and the mythology, through the observations and the implications of this potential discovery. We'll explore how a massive planet could remain hidden for so long, like a cosmic game of hide-and-seek played out over billions of years. We'll consider what it might mean for our understanding of planetary formation, of the architecture of solar systems, of the very nature of discovery itself in an age where we think we've mapped everything worth mapping. It's a question that touches on some of the deepest aspects of human curiosity, our desire to know what lies beyond the next hill, beyond the next star, beyond the edge of what we call the known. Perhaps you're skeptical, and that's perfectly natural, even healthy when it comes to claims about undiscovered planets. After all, we've been fooled before by the gravitational ghosts of worlds that turned out not to exist. Remember planet Vulcan, the world astronomers were certain must orbit between Mercury and the Sun to explain peculiarities in Mercury's orbit. It took Einstein's theory of general relativity to show us that no such planet was needed, that the warping of space-time itself near our massive Sun was enough to create these orbital oddities. Or consider Planet X, the world Percival Lowell spent years searching for beyond Neptune, convinced that something massive was tugging at the ice giants. While his search eventually led to the discovery of Pluto, we now know that tiny Pluto couldn't possibly have been the massive Planet X he was looking for, and the orbital irregularities he thought he saw turned out to be measurement errors, phantoms in the data. But this time feels different, and I'll tell you why in the gentlest, most contemplative way possible. The evidence for Planet 9 doesn't come from just one observation or one research team. It emerges from multiple independent lines of investigation, from different telescopes, different scientists, different approaches to the same puzzling patterns in the outer solar system. It's as if the universe is trying to tell us something through a cosmic whisper, a gravitational murmur that we're only just learning how to hear. The story begins, as many great discoveries do, with something that didn't quite fit, with observations that made astronomers pause and say, "That's peculiar, that shouldn't be happening unless." In 2003, astronomers discovered Sedna, a distant world about 3/4 the size of Pluto, following an extraordinarily elongated orbit that takes it far beyond the Kuiper Belt, that ring of icy bodies beyond Neptune. Sedna's orbit was strange, so strange that it suggested something had pulled it into that unusual path, something massive that we couldn't see. Then came more discoveries: VP113 2012, GB174, and others, each following similarly unusual orbits, each adding another piece to a puzzle that was beginning to form a picture. These distant objects, these sentinels at the edge of our solar system, seemed to be clustering in a way that defied random chance. Their orbits aligned in a manner that suggested they were all being shepherded by the gravity of something massive, something that must be out there in the darkness, slowly, patiently herding these icy wanderers like a cosmic shepherd tending an invisible flock. The mathematical beauty of this hypothesis lies not just in its ability to explain what we observe, but in its predictive power. If Planet 9 exists with certain characteristics, orbiting at certain distances with a certain mass, then we should see specific effects on the orbits of known objects, and remarkably we do see exactly those effects. It's like watching the wind move through a field of wheat. You can't see the wind itself, but you can see its influence. You can trace its path by the way the wheat bends and sways. In the same way, we can't yet see Planet 9 directly, but we can see its gravitational influence written in the orbits of distant worlds, a signature as unique as a fingerprint, as distinctive as a voice calling out from the darkness. Now, here's where our contemplation takes that intriguing turn I mentioned earlier. The initial calculations suggested that Planet 9, if it exists, orbits at an average distance of about 600 astronomical units from the Sun. To put that in perspective, 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking about a world that would be, on average, 600 times farther from the Sun than we are, a distance so vast that light from the Sun would take over 80 hours to reach it. At that distance, the Sun would appear as little more than a very bright star, unable to warm this frozen world above the most frigid temperatures imaginable. But what if those initial calculations, while not wrong exactly, were incomplete? What if they captured only part of the picture, like trying to understand the shape of an iceberg by looking only at what appears above the water? Recent refinements in the orbital models, new observations of additional distant objects, and more sophisticated computer simulations have begun to suggest something remarkable. Planet 9 might follow an extremely elliptical orbit, one that takes it very far from the Sun at its most distant point, but brings it much closer at its nearest approach. We're not talking about Venus or Mars close, mind you, but perhaps as close as 200 or 300 astronomical units, maybe even closer under certain orbital configurations. That might still sound impossibly far, and it is indeed a vast distance by human standards. But in cosmic terms, in terms of the scale of our solar system, it's practically in our backyard. It's the difference between something being in another country versus being on another continent, still far, but suddenly within the realm of future possibility for robotic exploration. Consider what this means for our chances of actually finding this world. At 600 astronomical units, Planet 9 would be so faint, so lost in the darkness, that even our most powerful telescopes would struggle to spot it among the countless background stars. But at 200 astronomical units, at that distance it becomes a much more feasible target, something that the next generation of telescopes might be able to detect, something that might already be hiding in existing survey data, waiting for the right pair of eyes, the right algorithm, the right moment of recognition. It's entirely possible that somewhere in the vast archives of astronomical observations, in the petabytes of data collected by surveys like Pan-STARRS or the Catalina Sky Survey, Planet 9 has already been photographed multiple times, recorded as just another faint point of light that no one recognized as special, because no one knew exactly where to look or what to look for. The implications ripple outward like waves on a cosmic pond. If Planet 9 is closer than we initially thought, it means our solar system is even more dynamic and complex than we imagined. It means that massive planets can maintain stable orbits in regions we thought were too chaotic, too disturbed by the gravitational influences of the known planets. It means that the process of planetary formation and migration in the early solar system must have been even more intricate, even more fascinating than our current models suggest. And perhaps most intriguingly, it means that Planet 9 might have been influencing the inner solar system, including Earth, in subtle ways throughout our planet's entire history. Think about that for a moment. Let it settle into your consciousness, like a stone dropping into still water. For the entire history of life on Earth, from the first simple cells to the dinosaurs to the emergence of humanity, this hidden giant might have been out there, completing its slow orbits, occasionally passing closer to the inner solar system and exerting gentle gravitational tugs that could have influenced everything from asteroid trajectories to the stability of the outer planets' orbits. We might have been living our entire existence as a species under the watchful gravitational eye of a world we didn't even know existed, a cosmic companion that has been with us all along, hidden in plain sight by the simple fact of its enormous orbit and our limited perspective. The search for Planet 9 represents something beautiful about human nature, our refusal to accept that we've discovered everything worth discovering, our persistent belief that mysteries remain to be solved, that wonders await us in the darkness. It's the same impulse that drove ancient humans to wonder what lay beyond the horizon, that inspired sailors to venture beyond sight of land, that compels us to send robotic emissaries to every corner of the solar system. We are, at our core, a species of explorers, and the possibility of an undiscovered planet in our own solar system calls to something deep within us, something that whispers, "There's more to find, Keep looking, keep wondering. As we continue our journey tonight, we'll explore the various lines of evidence that point to Planet 9's existence. We'll consider the alternative explanations that skeptics have proposed, and we'll imagine what this world might be like if it truly exists. We'll delve into the patient work of astronomers who spend night after night scanning the sky, looking for that telltale movement against the background stars that would announce the presence of a new world. We'll consider the technological challenges of finding something so faint, so distant, yet possibly closer than we ever dared hope. And we'll contemplate what it might mean for humanity's future if we confirm that our solar system has been hiding a massive ninth planet all along. But remember, this isn't a race to a conclusion. There's no urgency here. No need to reach the end of our contemplation quickly. Like the slow orbit of Planet 9 itself, if it exists, our exploration tonight can take its time, can meander through possibilities and implications, can pause to consider the beauty of the unknown and the wonder of discovery. Whether Planet 9 is eventually found or whether it remains forever a beautiful hypothesis, the search itself tells us something profound about who we are as a species, about our relationship with the cosmos, about our place in the grand architecture of space and time. So let yourself relax even more deeply now. Let your mind drift among the stars as we continue our peaceful exploration. There's something profoundly calming about contemplating the vastness of space, about recognizing that our daily worries and concerns, while important to us, exist within a much larger context of cosmic time and space. The universe has been here for nearly 14 billion years, and it will continue for billions more, and somewhere in that immensity of time and space, on a small blue planet orbiting an ordinary yellow star, we've evolved the capacity to wonder about worlds we've never seen, to search for planets we've only imagined, to reach out with our minds and our instruments toward the darkness and ask, what else is out there? Consider for a moment the vast emptiness between Neptune and the edge of our solar system, a region so immense that our minds struggle to truly comprehend its scale. If you were to travel at the speed of light, the fastest speed possible in our universe, it would take you over 4 hours just to reach Neptune from the Sun, and that's just the beginning of the journey into the outer darkness. Beyond Neptune lies a realm that makes the distances between the inner planets seem like mere footsteps in comparison. A void so vast that light itself, tireless and constant, takes hours, then days, then weeks to cross it. In this peaceful expanse, where the sun's warmth has faded to less than a whisper, and its light to barely more than the brightest star in the sky, thousands of icy bodies drift in eternal twilight, following strange orbital patterns that whisper of an unseen gravitational shepherd, a hidden giant that shapes their paths through the darkness. To truly appreciate the possibility that Planet 9 might be closer than we think, we need to understand the architecture of our solar system, the way it's structured, the way its various components interact across the vastness of space. Imagine, if you will, that we could compress the entire solar system down to a scale we could walk through, perhaps a large park or a small town. At this scale, the sun would be a glowing sphere about the size of a large beach ball at the center of our park. Mercury would be a tiny pebble, smaller than a pea, orbiting about 20 feet away. Venus, our beautiful morning star, would be a marble about 35 feet from our beach ball sun. Earth, our precious blue home with all its life and history, would be another marble, just slightly smaller than Venus, circling at about 50 feet. As we continue our walk outward through this scaled solar system, we pass Mars, a smaller marble with a reddish tint, about 75 feet from the centre. But then something remarkable happens to our sense of scale. To reach Jupiter, that massive giant that could swallow all the other planets combined, we need to walk about 250 feet from our beach ball sun, and Jupiter itself would be about the size of a softball. Saturn, with its beautiful rings, would be another softball, slightly smaller, about 500 feet away. Uranus and Neptune, the ice giants discovered in the age of telescopes, would be golf balls at 1,000 and 1,500 feet respectively. But here's where our walk becomes a journey, where the comfortable stroll through a park becomes an expedition into the unknown. The Kuiper Belt, that ring of icy bodies that includes Pluto and countless other frozen worlds, begins around where Neptune orbits and extends outward to perhaps twice that distance. In our scaled model, we're now half a mile from our beach ball sun, and we're just entering the realm where Planet 9 might lurk. The initial calculation suggested Planet 9 orbits at an average distance of 600 astronomical units, which in our scaled park would put it about 4 miles away from the centre, so far that you'd need a good pair of binoculars just to see the beach ball sun from there. But if Planet 9 follows an elliptical orbit that brings it as close as 200 astronomical units at its nearest approach, then in our model it would sometimes come within about 1.5 miles of the sun, still far, but close enough that you could walk there in about half an hour, close enough that it enters the realm of the reachable, the explorable, the discoverable. If you compress the entire history of our solar system into a single day, with the formation of the Sun and the protoplanetary disk beginning at midnight, the planets would have formed in the first few hours of that cosmic day. Earth would have cooled and developed its first oceans by early morning. Life would have appeared before noon, but complex multicellular life wouldn't emerge until evening. The dinosaurs would have ruled for just about an hour in late evening, and all of human civilization from the first agriculture to the present moment would occupy less than the last second before midnight. In this compressed timeline, humanity's search for Planet 9 would be an even tinier fraction of time, a moment so brief it could barely be measured. Yet in that infinitesimal instant, we've managed to gather clues suggesting something magnificent lurks in the darkness, perhaps closer than we ever dared imagine. The structure of our outer solar system tells a story written in ice and stone, in the frozen bodies that have circled our sun since the dawn of the planetary system. These objects, with names like Sedna, Eris, Makemake, and hundreds of others, are like archaeological artifacts from the solar system's youth, preserved in the deep freeze of space for billions of years. They follow a bewildering variety of orbits, some nearly circular, others stretched into extreme ellipses that take them far from the sun's influence. Some orbit in the same plane as the planets, while others follow tilted paths that take them high above and far below the ecliptic. It's in the patterns of these orbits, in the mathematical relationships between them, that we find our strongest evidence for Planet 9. You see, there's something peculiar about a subset of these distant objects, something that shouldn't happen by chance alone. About 12 of the most distant known objects in our solar system, bodies with orbits that take them beyond 250 astronomical units from the Sun, show a remarkable clustering in their orbital orientations. Their orbits seem to point in roughly the same direction, like compass needles influenced by an invisible magnetic pole. The probability of this alignment happening by random chance is less than 1%. perhaps as low as 0.007% according to some calculations. It's as if someone had thrown a handful of frisbees in a park, and instead of landing randomly, they all ended up pointing toward the same distant tree. A tree we can't see but whose presence we can infer from the arrangement of the frisbees. This clustering becomes even more intriguing when we consider not just the direction of these orbits, but their shapes and tilts as well. Many of these distant objects follow orbits that are inclined at similar angles to the plane of the solar system, and their orbital ellipses are oriented in space in ways that suggest they're all being influenced by the same massive unseen object. It's like watching a group of boats on a lake all drifting in the same direction, even though there's no visible current, or seeing leaves on different trees all leaning the same way, suggesting a prevailing wind we cannot feel. The gravitational influence of Planet 9, if it exists, would create exactly these kinds of patterns, shepherding these distant objects into similar orbital configurations over millions of years. But the architecture of our solar system holds even more clues, subtle hints written in the dynamics of objects we've known about for decades. There's a peculiar gap in the Kuiper belt, a region where we'd expect to find numerous objects but instead find relatively few. This gap could be explained by the gravitational influence of Planet 9, which would have cleared out this region over billions of years, either capturing objects into resonant orbits or flinging them into different trajectories entirely. It's similar to the gaps in Saturn's rings, those dark bands where the gravitational influence of tiny moons has swept the ring particles away, creating lanes of emptiness in what would otherwise be a continuous disk. The more we study the outer solar system, the more we realize how dynamic and complex it truly is. This isn't a realm of static, frozen bodies following unchanging orbits for eternity. Instead, it's a region of subtle gravitational dances, of slow migrations and patient reorganizations playing out over millions and billions of years. Objects in the Kuiper belt can be captured into resonances with Neptune, locked into orbital periods that form simple ratios with the ice giant's orbit. Some objects get flung inward to become comets that grace our night skies, while others are ejected entirely from the solar system, doomed to wander interstellar space forever. And through it all, if Planet 9 exists, it has been a hidden conductor, orchestrating parts of this cosmic symphony from the darkness. The very existence of certain types of orbits in the outer solar system poses puzzles that Planet 9 might solve. Take Sedna, for example, that distant world discovered in 2003. Sedna never comes closer to the Sun than about 76 astronomical units, well beyond the gravitational influence of Neptune. Yet its orbit is highly elliptical, taking it as far as 900 astronomical units from the Sun. How did Sedna end up in such an orbit? It's too far from Neptune to have been scattered by that planet, yet something must have put it on its current path. Planet 9, especially if it occasionally comes closer than initially thought, provides an elegant explanation. A close encounter with Planet 9 billions of years ago could have lifted Sedna into its current orbit, like a gravitational slingshot that sent this icy world on a journey to the edge of the solar system and back. The possibility that Planet 9 might be closer than we initially calculated opens up fascinating new scenarios for how it might interact with the known solar system. If its orbit is highly elliptical, bringing it within 200 astronomical units at closest approach, but taking it perhaps 1,000 astronomical units away at its most distant, Then it would spend most of its time in the far outer darkness, invisible and nearly impossible to detect. But during its closer approaches, which might happen every 10,000 or 20,000 years, its gravitational influence would be much stronger, potentially affecting the orbits of Kuiper Belt objects in ways we're only beginning to understand. It's like a cosmic visitor that drops by rarely, but leaves lasting impressions each time it passes through the neighborhood. Consider the implications of this orbital dance for the stability and evolution of our solar system. Over billions of years, Planet Nine's repeated passages through different regions of the outer solar system would have sculpted the distribution of small bodies we see today. Some objects would have been captured into stable resonances, their orbits locked in mathematical harmony with the giant planet. Others would have been scattered, sent on wild trajectories that might bring them into the inner solar system as comets, or eject them entirely. Still others might have been corralled into the clustered orbits we observe today, like sheep guided by an invisible shepherd. The architecture of our outer solar system in this view isn't just the result of the formation process billions of years ago, but an ongoing work of gravitational art with Planet Nine as one of the principal artists. The search for Planet Nine has also revealed just how much we still don't know about our cosmic neighborhood. Before this search began in earnest, many astronomers thought we had a fairly complete census of large objects in the solar system. Sure, we expected to find more Pluto-sized bodies in the Kuiper Belt, and we have, but a planet 5 to 10 times the mass of Earth? That seemed impossible to have missed. Yet the more we look, the more we realize that the outer solar system is vast beyond imagination, dark beyond our ability to easily probe, and full of surprises. Every year, new discoveries push the boundaries of what we know, revealing objects with ever more distant and unusual orbits, each one adding another piece to the puzzle of our solar system's architecture. The tools we use to map this architecture have evolved dramatically in recent decades. Modern telescopes equipped with sensitive digital cameras can detect objects far fainter than anything visible to earlier generations of astronomers. Computer algorithms can sift through millions of images, looking for the telltale motion that distinguishes a solar system object from a background star. Sophisticated numerical simulations can model the gravitational interactions of thousands of bodies over billions of years, revealing patterns and possibilities that would be impossible to calculate by hand. We're like explorers who've suddenly been given night vision goggles and GPS systems to explore a dark forest we previously could only stumble through blindly. Yet even with all these technological advances, the outer solar system guards its secrets jealously. The distances are so vast, the objects so faint, the sky so full of stars, that finding Planet Nine, if it exists, remains one of the most challenging quests in modern astronomy. If it's at 200 astronomical units, it would be about 40,000 times fainter than Neptune, itself barely visible to the naked eye under perfect conditions. If it's at 600 astronomical units, it would be nearly 400,000 times fainter, a ghostly point of light lost among millions of background stars. It's like trying to spot a single specific grain of sand on a beach at night, using only a flashlight, while not even knowing which section of beach to search. The architecture of our solar system also connects to larger questions about planetary systems in general. As we've discovered thousands of planets orbiting other stars, we've learned that our solar system, which once seemed like it must be typical, might actually be rather unusual. Many other systems have giant planets orbiting very close to their stars, or planets in highly elliptical orbits, or systems with completely different architectural arrangements than our own. If Planet 9 exists, especially if it's on an eccentric orbit that brings it relatively close at times, it would add another layer of complexity to our understanding of how planetary systems form and evolve. It might suggest that the migration and rearrangement of planets in the early solar system was even more dramatic than we thought, or that our solar system has been influenced by close encounters with other stars over its billions of years of orbiting the galaxy. As we contemplate these vast scales and ancient processes, there's something deeply peaceful about recognizing our place in this grand architecture. We live on a small world, orbiting an ordinary star, in a galaxy with hundreds of billions of other stars, many with their own planetary systems. Yet from this tiny vantage point, using the power of human curiosity and ingenuity, we're able to map the architecture of our cosmic neighborhood, to detect the gravitational whispers of worlds we cannot see, to piece together the history of our solar system from the orbits of icy bodies in the darkness. Whether Planet 9 is eventually found at 200 astronomical units, 600 astronomical units, or remains forever a beautiful hypothesis, the search itself reveals the remarkable fact that we, products of cosmic evolution, have developed the ability to comprehend the very cosmos that created us. Scientists have observed something remarkable in the outer reaches of our solar system, a pattern so subtle that it took years of careful observation and analysis to recognize, yet so striking that once seen, it cannot be ignored. Like detectives piecing together clues at a cosmic crime scene, astronomers have noticed peculiar clustering in the orbits of distant Kuiper belt objects, those frozen worlds that drift through the darkness beyond Neptune. These icy wanderers, some as large as Pluto, others no bigger than mountains, seem to move in harmony, their paths aligned in ways that defy random chance, as if they're all dancing to the same gravitational tune, following the lead of an invisible partner whose presence we can only infer from the synchronized movements of its companions. The story of these orbital whispers begins with patient observation, with astronomers spending countless nights at telescopes, tracking faint points of light as they slowly drift against the background of stars. Each of these distant objects takes centuries or even millennia to complete a single orbit around the Sun, so we can only observe tiny fractions of their journeys, like trying to understand the plot of a movie by watching just a few random frames. Yet from these brief glimpses, using the elegant mathematics of celestial mechanics, we can reconstruct entire orbits, predicting where these objects have been and where they're going with remarkable precision. It's a testament to the power of physics that we can take a few observations spread over a handful of years and extrapolate orbital paths that stretch across billions of miles and thousands of years. The Subaru telescope in Hawaii, perched atop Mauna Kea where the air is thin and the seeing is extraordinary, has been one of our primary windows into this distant realm. With its 8.2-meter mirror and sophisticated instruments, Subaru can detect objects so faint that they're millions of times dimmer than anything visible to the naked eye. Night after night, astronomers use this magnificent instrument to scan sections of sky, looking for the almost imperceptible motion that betrays the presence of a solar system object against the static backdrop of stars. Other observatories have joined this patient search. The Gemini telescopes, the Very Large Telescope in Chile, the Keck Observatory, each contributing observations that add pieces to our growing puzzle of the outer solar system's architecture. data from these telescopes reveal patterns that suggest a massive planet, perhaps 5 to 10 times Earth's mass, orchestrating this celestial ballet from the darkness. The evidence comes not from seeing this planet directly, not yet anyway, but from the gravitational influence it appears to exert on smaller bodies we can observe. It's like deducing the presence of a massive boulder in a stream by watching how the water flows around it, or inferring the existence of a large predator by observing the coordinated movement of a herd avoiding an unseen threat. The mathematics of these orbital alignments points consistently toward the same conclusion, that something massive is out there, shepherding these distant objects into their peculiar configurations. Let's delve deeper into what makes these orbital patterns so compelling. When astronomers look at the most distant known objects in our solar system, those with orbits that take them beyond 250 astronomical units from the Sun, they notice several remarkable coincidences. First, the long axes of their elliptical orbits, what astronomers call the major axes, tend to point in roughly the same direction in space. This is strange because over billions of years, we'd expect these orientations to be randomized by gravitational perturbations from the giant planets. Second, these orbits are tilted at similar angles relative to the plane of the solar system, as if something has lifted them in a coordinated fashion. Third, and perhaps most intriguingly, there's another population of distant objects whose orbits are tilted nearly perpendicular to the solar system's plane, and Planet 9's gravity could explain these as well. The probability calculations are what really make scientists sit up and take notice. When you have one or two objects with aligned orbits, it could easily be coincidence. But when you have 6, 8, 10 objects all showing similar alignments, the odds of this happening by chance become vanishingly small. Some calculations put the probability at less than 0.007%. Others suggest it might be as low as 0.001%. In science, when you see patterns with such low probabilities of occurring randomly, it usually means there's an underlying cause, a physical mechanism creating the pattern. In this case, that mechanism appears to be the gravity of an unseen planet, slowly but persistently herding these distant objects into aligned configurations over millions of years. What makes this evidence even more compelling is that it comes from multiple independent research groups using different methods and data sets. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown published their landmark paper presenting evidence for Planet 9. But they weren't the only ones seeing these patterns. Astronomers in Japan, Canada, the United Kingdom and elsewhere have conducted their own analyses, and while they might differ on some details, the overall picture remains consistent. Something massive appears to be influencing the orbits of distant solar system objects. This convergence of independent investigations gives scientists confidence that they're seeing a real phenomenon, not just a statistical fluke or observational bias. The dance of these distant objects tells us not just that Planet 9 might exist, but also provides clues about its properties. By analyzing exactly how these known objects are clustered, astronomers can work backward to determine what kind of planet would create such patterns. The calculations suggest Planet 9 has a mass between 5 and 10 times that of Earth, making it a super-Earth or mini-Neptune, types of planets that are actually quite common around other stars but conspicuously absent from our inner solar system. Its orbit appears to be tilted about 30 degrees from the solar system's plane, and stretched into an elongated ellipse that takes it far from the Sun at its most distant point, but brings it closer, perhaps much closer than initially thought, at its nearest approach. Consider what this means for the gravitational choreography of the outer solar system. Planet 9, if it exists, wouldn't affect distant objects constantly or uniformly. Instead, its influence would wax and wane as it travels its elongated orbit, stronger when it's closer to the inner solar system, weaker when it's in the distant reaches of its path. Objects that happen to be in the right place at the right time might receive a gravitational boost that sends them into new orbits, while others might be captured into resonances, their orbital periods locked in simple ratios with Planet 9's orbit. Over billions of years, this complex gravitational dance would create the patterns we observe today, like a cosmic choreographer whose work we can only appreciate by watching the dancers, never seeing the choreographer directly. The search for additional evidence has led astronomers to re-examine old observations with new eyes. The WISE Space Telescope, which surveyed the entire sky in infrared light, might have captured Planet 9 without anyone realizing it. The challenge is that Planet 9 would appear as just another faint point of light among millions of stars and galaxies, distinguishable only by its slow motion across the sky. Teams of researchers are now sifting through this archival data, using sophisticated algorithms to look for objects with the right combination of brightness and motion to be Planet 9. It's like searching through years of security camera footage for a person you've never seen, knowing only their approximate height and the fact that they were walking, not standing still. What if Planet 9 is already in our data, captured multiple times by different surveys but never recognized as a single object? This is entirely possible, even likely. Sky surveys typically observe the same regions of sky multiple times, but these observations might be separated by days, months, or even years. An object as distant as Planet 9 would move so slowly that it might appear in different positions in different surveys without anyone realizing they're looking at the same object. Connecting these dots requires careful analysis and sophisticated software, but the possibility that Planet 9 is already documented, waiting to be discovered in existing data, adds an element of tantalizing possibility to the search. The influence of Planet 9 might extend beyond just the distant Kuiper Belt objects. Some astronomers have suggested that the subtle tilt of the entire solar system's plane, relative to the Sun's equator, about 6 degrees, could be explained by Planet 9's gravitational influence over billions of years. If Planet 9 exists on a tilted orbit and has been part of our solar system since its early days, its gravity would have slowly torqued the orbital planes of the other planets, creating the misalignment we observe today. It's a bold hypothesis, but it demonstrates how a single hidden planet could have far-reaching effects on the entire solar system's architecture. Recent observations have added new layers to this cosmic mystery. Astronomers have discovered additional distant objects whose orbits fit the Planet 9 hypothesis, strengthening the statistical case for its existence. But they've also found some objects that don't fit the pattern as neatly, reminding us that the outer solar system is complex and that our understanding is still evolving. Science is rarely a straight path from hypothesis to confirmation. It's more like a winding trail with false starts, dead ends, and unexpected vistas. The search for Planet 9 embodies this beautifully, each new discovery adding nuance to our understanding, sometimes supporting the hypothesis, sometimes challenging it, always deepening our knowledge of the cosmic dance playing out in the darkness. The technological challenges of detecting Planet 9 directly are formidable but not insurmountable. If it's closer than initially thought, perhaps at 200 or 300 astronomical units, rather than 600, it becomes a much more feasible target for current and upcoming telescopes. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is set to begin operations soon, and it will survey the entire visible sky every few nights with unprecedented sensitivity. If Planet 9 is out there and within range, Vera Rubin should find it within its first few years of operation. The anticipation in the astronomical community is palpable, like waiting for the curtain to rise on a cosmic performance we've been expecting but have never seen. Amateur astronomers have also joined the hunt, participating in citizen science projects that harness the power of thousands of eyes to examine telescope images. Projects like Backyard Worlds, Planet 9 invite anyone with an internet connection to help search for moving objects in infrared images from the WISE telescope. It's entirely possible that Planet 9 will be discovered not by a professional astronomer at a major observatory, but by a retired teacher in Ohio or a student in Bangladesh, someone who notices a faint dot moving against the stars and realizes they're looking at a new world. The democratization of astronomical discovery adds a beautiful human element to this cosmic quest. As we contemplate these orbital whispers, these gravitational murmurs from the outer darkness, we're reminded of how much detective work goes into understanding our cosmic neighborhood. Every distant object we discover, every orbit we calculate, every pattern we recognize brings us closer to understanding whether Planet 9 really exists, and if so, where it might be hiding. The evidence from the orbital dance of distant objects is compelling, but not yet conclusive, like hearing footsteps in the dark and trying to determine who or what is making them. We know something is influencing these distant worlds. The question is whether it's a single massive planet, multiple smaller planets, or some other phenomenon we haven't yet considered. The implications of finding Planet 9 closer than expected ripple through multiple fields of astronomy and planetary science. It would affect our models of planetary migration in the early solar system, our understanding of how super-Earths and mini-Neptunes form, our theories about the delivery of water and organic molecules to the inner solar system, and our calculations of the solar system's long-term stability. Each of these topics connects to fundamental questions about our origins and our future, about how Earth became habitable, and whether our solar system's configuration is stable over billions of years. Planet 9, if it exists, isn't just another world to add to our solar system's roster. It's a key that could unlock deeper understanding of planetary systems throughout the universe. The mathematical beauty of the Planet 9 hypothesis lies in its elegance and simplicity. Rather than requiring multiple explanations for different phenomena, the existence of a single massive planet can potentially explain the clustering of distant orbits, the existence of perpendicular orbits, the truncation of the Kuiper belt, and even the solar system's tilt. In science, such unifying explanations are particularly attractive because they suggest we're seeing a fundamental truth rather than a collection of coincidences. It's like finding a single key that opens multiple locks, suggesting that the locks were all made by the same craftsman. Yet we must also remain open to alternative explanations, to the possibility that what we're interpreting as the influence of a single massive planet might be something else entirely. Perhaps there are multiple smaller planets creating these effects collectively. Perhaps there was a planet that has since been ejected from the solar system, its gravitational ghost still visible in the orbits it influenced billions of years ago. Perhaps there are aspects of gravity or dynamics in the outer solar system that we don't fully understand. Good science requires us to hold our hypotheses lightly, to follow the evidence wherever it leads, to remain excited about the possibility of Planet 9 while being prepared for whatever truth the universe reveals. In the quiet calculations of orbital mechanics, numbers tell stories of invisible forces shaping the cosmic dance, revealing truths that our eyes alone could never perceive. Mathematics, that universal language that transcends human cultures and even species, becomes our tool for peering into the darkness, for understanding the movements of worlds we cannot see, for predicting where a hidden planet might lurk based solely on its gravitational influence on objects we can observe. The equations that govern planetary motion, refined over centuries from Kepler through Newton to Einstein, allow us to work backward from effect to cause, from the observed perturbations in distant orbits to the mass and location of their unseen shepherd. It's a kind of cosmic forensics, where instead of fingerprints and DNA, we have orbital elements and gravitational signatures, each as unique and telling as any evidence in a detective's case file. Computer simulations run thousands, even millions of scenarios, each one exploring where Planet 9 might hide and how close it could venture to the realm of the known planets. These aren't simple calculations that could be done with pencil and paper. They require massive computational power, supercomputers running for weeks or months, testing different masses, different orbits, different distances to see which combinations best explain the patterns we observe. Each simulation starts with the known planets and the observed distant objects, then adds a hypothetical Planet 9 with specific properties, and watches how the system evolves over millions or billions of simulated years. It's like running the history of the solar system in fast forward, watching eons pass in hours, seeing how gravity slowly sculpts the orbits of distant worlds into the configurations we observe today. Perhaps the most intriguing possibility emerging from these mathematical models is that Planet 9 follows an orbit so tilted, so unusual, that we've been looking in all the wrong places. Most planets orbit roughly in the same plane, like marbles rolling on a flat table, but Planet 9 might be on an orbit tilted 30 degrees or more from this plane, like a marble rolling on a ramp that cuts across the table at an angle. This means that for much of its orbit, Planet 9 would be high above or far below the regions of sky, where astronomers typically search for solar system objects. It's as if we've been searching for a bird by looking along the ground, not realizing it spends most of its time in the treetops. This tilted orbit isn't just a random possibility. It emerges naturally from the mathematics when we try to explain the observed clustering of distant objects. Consider that this world might swing as close as 200 astronomical units at its nearest approach, a distance that, while still vast by human standards, is close enough that future space telescopes might glimpse its faint reflection of sunlight. At 200 astronomical units, Planet 9 would be about 40,000 times fainter than Neptune, pushing the limits of our current technology but not beyond them. The mathematics of light and distance follow an unforgiving inverse square law, meaning that doubling the distance makes an object 4 times fainter, tripling it makes it 9 times fainter, and so on. This is why the difference between Planet 9 being at 200 AU versus 600 AU is so crucial. At the closer distance, it's challenging but possible to detect, At the farther distance, it becomes exponentially more difficult, like trying to spot a candle flame from across a city versus from across a country. The mathematical models also tell us about Planet 9's likely composition and appearance. A planet of 5 to 10 Earth masses at that distance from the Sun would likely be what astronomers call a sub-Neptune or super-Earth, a type of planet that's actually the most common in the galaxy, but mysteriously absent from our inner solar system. It would probably have a rocky or icy core surrounded by a thick atmosphere of hydrogen and helium, perhaps with exotic clouds of methane or ammonia, crystals. The mathematics of planetary physics suggests it would still be warm inside from the heat of its formation, radiating more energy than it receives from the sun, glowing faintly in infrared light like a dying ember in a cosmic fireplace. This internal heat is crucial for detection. It means Planet 9 might be easier to spot in infrared telescopes than in visible light, its own warmth making it stand out against the cold background of space. The orbital dynamics of Planet 9, if it exists, would be a masterclass in celestial mechanics. Its elongated orbit would take it through dramatically different regions of the solar system, from the relatively crowded Kuiper belt to the nearly empty void beyond. As it moves along this path, its velocity would change dramatically, moving fastest when closest to the Sun, following Kepler's laws with mathematical precision, then slowing to a crawl at its most distant point. The mathematics tells us that if Planet 9's orbit takes it from 200 astronomical units to 700 astronomical units, it would spend most of its time in the outer portions of its orbit, moving slowly through the darkness, which partly explains why it's been so hard to find. It's like a cosmic game where the target spends 90% of its time in the hardest to search areas. The resonances that Planet 9 might create with other objects are particularly fascinating from a mathematical perspective. Orbital resonances occur when two objects have orbital periods that form simple integer ratios, like 2:1 or 3:2, creating a gravitational relationship that can stabilize or destabilize orbits over long periods. The mathematics of these resonances is beautiful in its simplicity and powerful in its effects. Objects caught in resonance with Planet 9 would have their orbits shaped and maintained by repeated gravitational interactions, like a child on a swing being pushed at just the right moment to maintain their motion. These resonances create a kind of gravitational architecture in the outer solar system, invisible lanes and boundaries defined not by physical barriers, but by the mathematics of orbital dynamics. Statistical analysis plays a crucial role in building confidence in the Planet 9 hypothesis. When astronomers say there's less than a 0.007% chance that the observed orbital clustering is random, they're using sophisticated statistical methods to quantify uncertainty. These calculations take into account not just the orbits we see, but also our observational biases, where we've looked, how long we've looked, what we might have missed. It's like trying to determine if a coin is fair by flipping it a limited number of times while acknowledging that you might be more likely to record heads than tails for some reason. The mathematics must account for all these factors to give us a true picture of how likely or unlikely the observed patterns are. The computational challenges of finding Planet 9 are staggering when you consider the numbers involved. The sky contains about 41,000 square degrees, and Planet 9 could be in any of them. If it takes an hour of telescope time to search 1 square degree to the necessary depth, that's nearly 5 years of continuous observation to search the entire sky. But it's worse than that because Planet 9 is moving, so you need multiple observations of each area to detect its motion, and you need to distinguish it from millions of background stars, any of which might be variable or have their own proper motion. The mathematics quickly becomes overwhelming, which is why sophisticated algorithms and massive computing power are essential for the search. Machine learning and artificial intelligence are now being brought to bear on this problem, trained on simulated data to recognize the subtle signature of a distant moving planet among the noise of stars and galaxies. These algorithms can process vast amounts of data far faster than humans, looking for patterns that might escape even trained astronomers. The mathematics underlying these AI systems, neural networks with millions of parameters, optimization algorithms that adjust and learn, represents a new frontier in astronomical discovery. It's possible that Planet 9 will be found not through traditional observation, but through an AI system recognizing a pattern in data that humans had looked at but not truly seen. The gravitational influence of Planet 9 would extend far beyond just the objects we've observed. Mathematical models suggest it would create a kind of gravitational wake as it moves through its orbit, subtly influencing the trajectories of comets, asteroids, and smaller planets over millions of years. These influences would be tiny for any individual object, but could accumulate over time to create observable effects. Some researchers have suggested that Planet 9 might be responsible for the occasional delivery of comets from the outer solar system to the inner planets, potentially influencing the rate of impact events on Earth over geological timescales. The mathematics of these interactions is complex, involving what physicists call the three-body problem, which has no general analytical solution and must be solved numerically for each specific case. The possibility that Planet 9 might be a captured rogue planet adds another layer of mathematical intrigue. Rogue planets, worlds that have been ejected from their original solar systems, are thought to be common in our galaxy, perhaps outnumbering stars. The mathematics of gravitational capture is delicate, requiring just the right approach, velocity and angle for a passing rogue planet to be captured into orbit around our Sun, rather than flying past or colliding with another planet. If Planet 9 was captured, its unusual orbit would make more sense. It would retain some memory of its interstellar trajectory and its tilted, elongated path around our Sun. The probability calculations for such a capture are low, but not impossibly so, especially in the early solar system when the Sun was still part of its birth cluster of stars. The long-term stability of Planet 9's orbit is another mathematical puzzle. For a planet to have survived in its current orbit for billions of years, that orbit must be stable against perturbations from the other planets, passing stars, and the galactic tide. Numerical simulations extending over the age of the solar system show that certain orbital configurations for Planet 9 would be stable while others would not. This constrains where Planet 9 could be, eliminating some regions of parameter space and focusing the search on others. It's like knowing that a hidden treasure must be in a place where it wouldn't have been washed away by erosion over the centuries, narrowing down the search area based on geological mathematics. The effect of Planet 9 on the solar system's invariable plane is particularly elegant mathematically. The invariable plane is defined by the total angular momentum of the solar system, and it's slightly tilted relative to the Sun's equator. If Planet 9 exists with the proposed mass and orbit, it would contribute significantly to the solar system's total angular momentum, potentially explaining this tilt. The mathematics is straightforward in principle but complex in detail, requiring careful calculation of angular momentum vectors and their evolution over time. It's a beautiful example of how a single hidden object could influence the entire system's orientation in space. As we delve deeper into these mathematical mysteries, we encounter concepts that push the boundaries of our intuition. The phase space of possible orbits for Planet 9 is vast and multidimensional, each point representing a different combination of orbital elements: semi-major axis, eccentricity, inclination, argument of perihelion, longitude of ascending node, and mean anomaly. Searching this phase space efficiently requires sophisticated optimization algorithms that can identify regions of high probability and focus computational resources there. It's like searching for a needle in a haystack, but the haystack has 6 dimensions and the needle is moving. The interplay between analytical and numerical methods in studying Planet 9 showcases the power of modern computational astronomy. While we can write down the equations that govern planetary motion, solving them for a system with multiple planets over billions of years requires numerical integration, stepping forward in time increment by increment, calculating forces and accelerations at each step. The choice of integration method, time step, and numerical precision all affect the accuracy and efficiency of these calculations. Too large a time step and you miss important interactions. Too small and the computation takes forever. It's a delicate balance that requires both mathematical sophistication and practical judgment. What if Planet 9 has been visiting the inner solar system for billions of years, leaving subtle marks on the worlds we know, like an ancient traveller whose footprints can still be traced in stone long after they've passed? This possibility opens up a fascinating window into deep time, into the idea that our Earth and Moon, the other planets, even the asteroids and comets, might carry within their geological and orbital histories the evidence of close encounters with this hidden giant. Some scientists wonder if ancient crater patterns on the Moon might record periodic gravitational disturbances from Planet 9's closer passages, preserved in the lunar surface like a cosmic diary written in impacts and overlapping circles of destruction and creation. The Moon, after all, has no atmosphere, no weather, no plate tectonics to erase its history. Every major impact from the last 4 billion years is still visible, waiting to tell its story to those who know how to read it. The geological record of Earth itself might hold clues, though they would be far more subtle and difficult to interpret than those on the Moon. Consider that Planet 9, if it follows an orbit that brings it within 200 astronomical units every 10,000 to 20,000 years, would have completed hundreds of thousands of orbits since Earth formed. Each close approach wouldn't cause dramatic immediate effects. The gravitational influence at that distance would be far too weak to trigger earthquakes or volcanic eruptions directly. But over geological timescales, these repeated gentle tugs might influence the delivery rate of comets from the outer solar system, potentially affecting the frequency of impact events that have played such crucial roles in Earth's history. Some researchers have looked for periodicities in extinction events, in crater formation rates, in the geological record of climate changes, searching for patterns that might match Planet 9's orbital period. The sediment layers in ancient ocean beds tell stories that span millions of years, and within these layers, scientists have found evidence of periodic changes that don't quite match the known cycles of Earth's orbit and rotation. The Milankovitch cycles, those variations in Earth's orbit and tilt that drive ice ages, are well understood and account for many of the patterns we see. but there are other, subtler variations that remain unexplained. Periodicities that might, just might, reflect the gravitational influence of a distant massive planet sweeping through its elongated orbit. It's like finding a rhythm in a piece of music that doesn't match the main beat, suggesting another instrument playing softly in the background, barely audible, but definitely there. In the cosmic library of our solar system's history, perhaps we've been reading the footnotes of Planet 9's influence all along without recognizing them for what they are. The asteroid belt, that collection of rocky debris between Mars and Jupiter, shows gaps and concentrations that we've long attributed solely to Jupiter's gravitational influence. But what if Planet 9 has also played a role? Its periodic passages through the outer solar system sending waves of perturbations inward that affected the asteroid belt structure over billions of years. Computer simulations suggest that a massive outer planet could indeed influence the asteroid belt, creating subtle patterns in the distribution of asteroids that we're only now beginning to have the computational power to recognize and understand. The Oort cloud, that vast spherical shell of icy bodies surrounding our solar system at distances of thousands to tens of thousands of astronomical units, might be particularly sensitive to Planet 9's influence. If Planet 9's orbit takes it from 200 to 700 astronomical units, or even farther, it would periodically pass through or near the inner edge of the Oort cloud, potentially disturbing comets and sending them toward the inner solar system. This could create waves of cometary activity, periods when Earth and the other planets experience more comet impacts, followed by quieter periods when Planet 9 is in a different part of its orbit. Some researchers have suggested that mass extinction events on Earth might correlate with these waves of comets, though the evidence remains controversial and heavily debated. The idea that Planet 9 might have influenced the evolution of life on Earth is both fascinating and sobering. Major impact events have played crucial roles in life's history, from the late heavy bombardment that may have delivered water and organic molecules to early Earth, to the asteroid impact that ended the reign of the dinosaurs 66 million years ago. If Planet 9 has been modulating the rate of these impacts through its gravitational influence on comets and asteroids, then this hidden world has been an unseen player in the story of life on Earth. We might owe our very existence to the orbital dynamics of a planet we've never seen, a cosmic puppet master pulling gravitational strings from the darkness. The cratering record on the Moon provides one of our best windows into the impact history of the Earth-Moon system. Unlike Earth, where erosion and plate tectonics constantly erase old craters, the Moon preserves impacts from billions of years ago. Some researchers have analysed the ages and distributions of lunar craters, looking for patterns that might indicate periodic increases in the impact rate. While the data is noisy and interpretations vary, there are tantalizing hints of periodicities that don't match any known solar system cycles. Could these be the signature of Planet 9's influence recorded in rock and regolith for billions of years? The upcoming Artemis missions to the Moon might provide new samples and data that could help answer this question. The possibility that Planet 9 has been influencing our solar system throughout its history raises profound questions about planetary system evolution in general. If our solar system has harboured a massive hidden planet all along, how common might such arrangements be? Around other stars? The thousands of exoplanetary systems we've discovered show a bewildering variety of configurations, many quite different from our own. Perhaps hidden planets on distant eccentric orbits are common, and we're only now developing the techniques to detect their subtle influences. This would mean that our understanding of planetary systems is still incomplete, that there might be entire populations of planets we haven't yet learned to see. Consider the role Planet 9 might have played in the late heavy bombardment, that period about 3.9 billion years ago, when the inner solar system experienced an intense rain of asteroids and comets. The standard explanation involves the migration of Jupiter and Saturn, but what if Planet 9 was also involved? Its gravitational influence could have destabilized orbits in the outer solar system, contributing to the cascade of impacts that reshape the surfaces of the Moon, Mars, Mercury, and Earth. Those impacts might have delivered water and organic molecules crucial for life's emergence, meaning that Planet 9, if it exists, could have been instrumental in making Earth habitable. The orbital evolution of the solar system over billions of years is a complex dance involving all the planets, and adding Planet 9 to this dance changes the choreography in subtle but important ways. Numerical simulations that include a massive outer planet show that it could have influenced the migration patterns of the giant planets, affected the stability of the asteroid belt, and modified the delivery of volatile rich materials to the inner solar system. These effects wouldn't be dramatic or catastrophic, but rather gentle nudges accumulated over eons, slowly shaping the solar system into its current configuration. It's like watching a river carve a canyon. No single moment is dramatic, but the cumulative effect over geological time is profound. The climate history of Earth, recorded in ice cores, ocean sediments, and rock formations, shows variations on many different timescales. While most of these can be explained by known factors like volcanic eruptions, variations in solar output, and changes in Earth's orbit, there remain some mysterious periodicities that lack clear explanations. Could some of these be related to Planet 9's orbital cycle? If Planet 9 influences the delivery of comets to the inner solar system, and if some of these comets impact Earth or deposit dust in the upper atmosphere, they could affect climate in subtle ways. It's a speculative idea, but one that demonstrates how a hidden planet could leave its fingerprints throughout Earth's geological record. The distribution of long-period comets, those that take hundreds or thousands of years to orbit the Sun, provides another potential record of Planet 9's influence. These comets come from the Oort cloud, and their orbits should be randomly distributed if nothing is perturbing them. But observations show some clustering and patterns that don't quite match random distribution. Planet 9, passing through or near the inner Oort cloud, could create these patterns, shepherding comets into preferred orbital configurations. By studying the orbits of long-period comets, we might be able to trace Planet 9's path through the outer solar system over the past few million years, like following breadcrumbs through a cosmic forest. The possibility that Planet 9 is a captured rogue planet adds another layer to its potential influence on solar system history. If it was captured early in the solar system's history, perhaps when the Sun was still part of its birth cluster, the capture event itself could have had dramatic effects. The gravitational disturbance of a massive planet being captured could have scattered smaller bodies throughout the solar system, potentially explaining some of the unusual orbits we observe today. It might have triggered a reorganization of the outer solar system, sending some objects inward as comets, while ejecting others entirely. The capture of Planet 9 could have been one of the defining events in our solar system's early history, shaping everything that came after. Ancient human civilizations looking up at the night sky without light pollution, without telescopes, with only their eyes and their wonder, might have occasionally seen comets that were sent our way by Planet Nine's gravitational influence. These cosmic visitors, with their glowing heads and streaming tails, were often interpreted as omens or messages from the gods. Little did our ancestors know that these celestial apparitions might have been messengers from a hidden world at the edge of our solar system, a planet that has been part of our cosmic neighborhood all along, but remained invisible to human eyes. The comets that inspired fear and awe, that were recorded in ancient texts and carved into stone, might have been Planet Nine's calling cards, sent from the darkness to remind us that there's more to our solar system than meets the eye. The extinction of the dinosaurs 66 million years ago, caused by a massive asteroid impact, is one of the most dramatic events in Earth's history. While we know the impactor came from the asteroid belt, the question of why it was perturbed into an Earth-crossing orbit remains open. Could Planet Nine have played a role? Through a complex chain of gravitational interactions, Planet Nine's influence could have destabilized the asteroid's original orbit, sending it on a collision course with Earth. If true, this would mean that Planet Nine has directly influenced the evolution of life on Earth, ending the age of dinosaurs and paving the way for the rise of mammals and eventually humans. We might owe our existence to a planet we've never seen. The delivery of water to Earth early in its history is another puzzle where Planet Nine might have played a role. Earth formed in a region of the solar system that was probably too hot for water ice to condense, so our oceans must have been delivered by impacts from water-rich asteroids and comets. The timing and source of this water delivery is still debated, but Planet Nine's gravitational influence could have affected both. By perturbing the orbits of water-rich bodies in the outer solar system, Planet Nine might have increased or decreased the rate of water delivery to Earth, potentially influencing when and how our planet became habitable. Every glass of water we drink, every drop of rain that falls, might exist because of gravitational interactions involving a hidden planet billions of years ago. As we contemplate these ancient echoes and cosmic memories, we're reminded of the interconnectedness of everything in our solar system. No planet is an island. Each world influences and is influenced by all the others through the patient work of gravity over billions of years. Planet Nine, if it exists, has been part of this cosmic web all along, an invisible thread connecting distant comets to Earth impacts, linking the outer darkness to the inner light, binding the history of our world to the movements of a planet we're only now beginning to suspect exists. Whether Planet Nine is eventually found or remains forever a hypothesis, the search for its ancient influence teaches us to look at our solar system's history with new eyes, to see patterns and connections we might have missed, to appreciate the deep time over which planetary systems evolve and change, the sedimentary rocks of Earth, the craters of the Moon, the orbits of comets and asteroids. All these are pages in a book that tells the story of our solar system. Planet Nine, if it exists, has been one of the authors of this story, writing its chapters in gravitational ink that takes billions of years to dry. As we learn to read these ancient texts more carefully, to decode the subtle messages written in stone and ice, and orbital dynamics, we might finally discover whether this hidden world has been with us all along, a silent companion in our journey around the galaxy, a cosmic neighbor we're only now getting to know. The search for Planet Nine is thus not just a search for a new world, but a search for a deeper understanding of our own world's history, for the hidden connections that bind all things in our solar system together across the vastness of space and the depths of time. Somewhere in the vast darkness, telescopes sweep methodically across star fields, their electronic eyes more sensitive than any human vision, searching for the telltale drift of a distant world against the stellar background. Night after night, in observatories perched on mountain tops where the air is thin and the seeing is steady, astronomers and their robotic assistants continue one of the most ambitious treasure hunts in the history of science. The Vera Rubin Observatory, that marvel of modern engineering and optics, prepares to map the entire sky with unprecedented sensitivity. Its 8.4-meter mirror and 3 billion pixel camera possibly ready to reveal what has remained hidden since the birth of our solar system. This magnificent instrument, when it begins its survey, will photograph the entire visible sky every few nights, creating a movie of the cosmos where anything that moves, anything that changes, will stand out like a firefly against the static stellar backdrop. This search for Planet 9 is unlike the discovery of any previous planet in our solar system. When William Herschel discovered Uranus in 1781, he was simply surveying the sky with his handmade telescope when he noticed a disk-like object that moved against the stars. When Neptune was discovered in 1846, astronomers knew almost exactly where to look based on mathematical predictions from Uranus's orbital perturbations. Even Pluto, found in 1930 after years of searching, was discovered by the patient methodical comparison of photographic plates, looking for a moving dot among the static stars. But Planet 9, if it exists, presents challenges that dwarf all previous planetary searches. It's fainter than anything previously discovered, potentially located anywhere across vast swathes of sky, and moving so slowly that detecting its motion requires observations separated by days or weeks. Amateur astronomers around the world have joined the hunt through citizen science projects, their enthusiasm and dedication adding thousands of eyes to the search. The Backyard Worlds Planet 9 project invites anyone with an internet connection to examine images from the WISE space telescope, looking for objects that move between frames taken months or years apart. It's a beautiful democratization of astronomical discovery, where a retired teacher in Japan, a student in Brazil, or a hobbyist in Germany might be the first person to spot humanity's ninth planet. The project has already discovered numerous brown dwarfs, those failed stars too small to sustain fusion, and while Planet 9 hasn't been found yet, each discovery helps map our cosmic neighborhood and eliminates places where Planet 9 isn't hiding. The technical challenges of this search push our current technology to its absolute limits. Planet 9, if it's at 200 astronomical units, would be about 40,000 times fainter than Neptune, which itself is barely visible to the naked eye under perfect conditions. If it's at 600 astronomical units, it would be nearly 400,000 times fainter, a ghostly point of light that would be invisible to all but the most powerful telescopes. To put this in perspective, imagine trying to spot a single specific firefly in a forest at night from several miles away, while millions of other fireflies, the background stars, are also glowing all around it. And you don't even know which section of forest to search, only that somewhere, maybe, that one special firefly is slowly drifting through the trees. The Subaru telescope in Hawaii has been conducting what's called the Hyper-Suprime Cam survey, using its wide field of view to search large areas of sky where Planet 9 might lurk. Each image from this survey covers an area of sky about the size of 9 full moons and can detect objects far fainter than what most telescopes can see. The data from these observations amounts to petabytes of information, far more than any human could examine manually. Sophisticated computer algorithms sift through this cosmic haystack, looking for the needle of Planet 9's motion. These algorithms must distinguish real moving objects from cosmic rays hitting the detector, from asteroids much closer to home, from variable stars that change brightness, from all the myriad things that can masquerade as a distant planet. What if Planet 9 is already captured in existing data, waiting patiently to be recognized, perhaps much closer in those images than anyone expected? This tantalizing possibility drives researchers to re-examine archival observations with fresh eyes and new techniques. The Sloan Digital Sky Survey, the Catalina Sky Survey, Pan-STARRS, and numerous other projects have photographed large portions of the sky over the past decades. Planet 9 might appear in these images as an unremarkable dot of light, its true nature revealed only when images taken at different times are compared to show its slow motion. It's entirely possible that multiple telescopes have already photographed Planet 9 without anyone realizing they were looking at the same object, like different witnesses describing the same person without knowing they're talking about the same individual. The role of artificial intelligence and machine learning in the search represents a new frontier in astronomical discovery. Neural networks trained on simulated data learn to recognize the subtle signature of a distant moving planet among the noise of stars, galaxies, and detector artifacts. These AI systems can process vast amounts of data far faster than humans, looking for patterns that might escape even trained astronomers. They can learn to ignore the types of false positives that plague traditional searches, becoming increasingly sophisticated at distinguishing real planets from the countless things that can mimic them. It's possible, even likely, that Planet 9 will be discovered not by a human looking through a telescope or even at a computer screen, but by an algorithm recognizing a pattern in data that humans had examined but not truly seen. The infrared sky offers another window in the search for Planet 9, one that might be especially promising if the planet is closer than initially thought. While Planet 9 would reflect very little sunlight at its enormous distance, it would still retain heat from its formation billions of years ago. This internal warmth would cause it to glow faintly in infrared light, potentially making it easier to detect with infrared telescopes than with visible light instruments. The WISE space telescope surveyed the entire sky in infrared wavelengths, and researchers continue to mine this data for signs of Planet 9. The challenge is that the infrared sky is full of objects, from distant galaxies to brown dwarfs to asteroids in our own solar system, all glowing with their own heat. Finding Planet 9 among all these heat sources is like trying to find a particular warm stone in a field full of warm stones on a summer evening. The upcoming Nancy Grace Roman Space Telescope, with its wide field of view and exquisite sensitivity, might be the instrument that finally spots Planet 9. This space telescope, free from the blurring effects of Earth's atmosphere, will be able to survey large areas of sky with unprecedented precision. If Planet 9 is within its detection limits, Roman should find it, potentially ending decades of speculation with a single observation. The anticipation in the astronomical community is palpable, like theatre-goers waiting for the curtain to rise on a long-awaited performance. Will Roman reveal a new world at the edge of our solar system, or will it show that Planet 9, if it exists, is even more elusive than we imagined? ground-based telescopes continue to play a crucial role in the search, with new instruments and techniques constantly expanding our capabilities. Adaptive optics systems that correct for atmospheric turbulence in real time allow ground-based telescopes to achieve nearly the same clarity as space telescopes. Wide-field cameras can survey large areas of sky quickly, while specialized instruments can detect the faintest objects. The Vera Rubin Observatory, when it comes online, will revolutionize our ability to find moving objects in the solar system. Its legacy, survey of space and time, will create a detailed movie of the sky, showing everything that moves or changes brightness over a 10-year period. If Planet 9 crosses the survey area during this time, Vera Rubin will find it. The coordination of the global search effort resembles a carefully orchestrated campaign, with different telescopes and teams focusing on different aspects of the problem. Some groups concentrate on finding more distant Kuiper belt objects, whose orbits might be influenced by Planet 9, adding to the statistical evidence for its existence. Others focus on direct searches in the most probable regions of sky. Still others work on improving the theoretical models, refining predictions of where Planet 9 should be based on the latest observations. This collaborative effort, spanning continents and cultures, represents humanity at its best, working together to solve a cosmic mystery that belongs to all of us. The psychological aspects of the search are as fascinating as the technical ones. Astronomers must maintain enthusiasm and focus while searching for something that might not exist. Examining thousands of images where Planet 9 almost certainly isn't present to find the one where it might be. It's the exercise in patience and persistence that would challenge anyone's dedication. Yet, the possibility of being the person who discovers a new planet in our solar system, the first such discovery in nearly a century if we count Pluto, drives researchers forward. The fame would be considerable, but more than that, it would be the satisfaction of solving one of astronomy's greatest current mysteries, of adding a new world to humanity's map of the solar system. False alarms are an inevitable part of any search for something at the edge of detectability. Several times, researchers have identified candidate objects that seem to match what Planet 9 should look like, only to find upon further observation that they were distant galaxies, variable stars, or other phenomena masquerading as a planet. Each false alarm is both a disappointment and a learning experience, helping researchers refine their search techniques and elimination criteria. The process resembles prospecting for gold, where many promising rocks turn out to be pyrite, fool's gold, but each false lead teaches the prospector more about what real gold looks like. The public engagement with the Planet 9 search has been remarkable, with people around the world following developments with intense interest. Social media lights up whenever a new paper is published or a new search campaign is announced. Online forums buzz with speculation and amateur analysis. This public interest isn't just passive observation. Through citizen science projects, members of the public are actively contributing to the search, examining images, running simulations on their home computers, and even conducting their own observations with amateur telescopes. The search for Planet 9 has become a shared human endeavor, a quest that captures something essential about our species' curiosity and our desire to explore the unknown. The technological advances driven by the Planet 9 search will have benefits far beyond finding or not finding this one world. The improved algorithms for detecting faint moving objects will help us find potentially hazardous asteroids that might threaten Earth. The massive surveys conducted in the search will create invaluable databases for all kinds of astronomical research. The machine learning techniques developed for Planet 9 will be applicable to other problems in astronomy and beyond. Even if Planet 9 is never found, the search for it will have advanced our capabilities and knowledge in numerous ways. As each night falls and telescopes around the world turn their eyes to the sky, the search continues with quiet persistence. Somewhere out there, perhaps closer than we ever imagined, a world 5 to 10 times the mass of Earth might be slowly drifting through the darkness, reflecting just enough sunlight or radiating just enough heat to be detected if we look in exactly the right place at exactly the right time. The search is like a cosmic game of hide and seek played out on the grandest possible scale, with one player hidden somewhere in a playing field that spans billions of miles. Every observation that doesn't find Planet 9 narrows down where it could be, bringing us incrementally closer to either discovery or the conclusion that it doesn't exist. The philosophical implications of the search are profound regardless of its outcome. If Planet 9 is found, especially if it's closer than expected, it will remind us that our cosmic neighborhood still holds major surprises, that our map of the solar system is still incomplete even after centuries of telescopic observation. If extensive searches fail to find Planet 9, that too will be valuable, forcing us to reconsider our interpretations of the orbital patterns in the outer solar system, perhaps leading to even more interesting discoveries. Either way, the search itself is expanding our knowledge, pushing our technology, and engaging people around the world in the grand adventure of astronomical discovery. Imagine Planet 9 not as a solitary wanderer drifting through the outer darkness, but as a mini-system unto itself, perhaps accompanied by moons, rings, or captured asteroids from its long journey through the outer solar system. If this hidden world exists, especially if it's closer than we initially thought, it might host a retinue of companions that would make it not just a planet but a destination, a whole new realm for exploration and discovery. These companions might be detectable too, adding their own faint light to Planet 9's glow, creating a system within our system. Worlds within worlds that have been orbiting together in the darkness for billions of years. The possibility transforms Planet 9 from a simple addition to our planetary roster into something far more intriguing, a complex system that might harbour its own mysteries, its own potential for surprising discoveries. Consider the possibility that this world might harbour subsurface oceans beneath layers of exotic ices, warmed by internal heat and tidal forces from its moons. At 5 to 10 times Earth's mass, Planet 9 would have substantial internal heat from its formation, radioactive decay in its core, and possibly ongoing gravitational contraction. This heat, trapped beneath insulating layers of ice and atmosphere, could maintain liquid oceans for billions of years. If Planet 9 has large moons, their gravitational tugging would create tidal heating, adding another energy source to keep these hidden oceans liquid. We've learned from Jupiter's moon Europa and Saturn's moon Enceladus that subsurface oceans can exist in the most unlikely places, maintained by tidal forces far from the sun's warmth. Planet 9's ocean, if it exists, would be the most remote and isolated body of liquid water in the solar system, a hidden sea in the cosmic darkness. In the peaceful solitude of the outer solar system, entire ecosystems of possibility drift quietly through the darkness. While the chances of life existing on or within Planet 9 are exceedingly remote, The mere possibility expands our conception of habitable environments. We've learned from extremophiles on Earth, those organisms that thrive in conditions once thought impossible for life, that biology is remarkably adaptable and persistent. Deep in Earth's oceans, around hydrothermal vents where no sunlight penetrates, entire ecosystems thrive on chemical energy. In the subsurface oceans of a world like Planet 9, similar chemistry might be possible. Hydrothermal vents on the ocean floor, powered by the planet's internal heat, could provide the chemical energy necessary for simple forms of life. It's a speculative idea, to be sure, but one that reminds us that life might find ways to exist in places we never imagined. The moon system of Planet 9, if it exists, would be a fascinating laboratory for understanding satellite formation and evolution. Large planets typically have extensive moon systems, formed through a combination of processes including direct formation from the circumplanetary disk, capture of passing objects, and collisions that create debris disks. Jupiter has 79 known moons, Saturn has 82, and even Neptune, far from the Sun, has 14. Planet 9, with 5 to 10 times Earth's mass, could easily support dozens of moons, ranging from large worlds comparable to Earth's moon down to tiny captured asteroids. These moons would have been shaped by billions of years of tidal forces, impacts, and gravitational interactions, each one a world with its own unique history and characteristics. The largest moons of Planet 9 might be substantial worlds in their own right, perhaps comparable in size to the major moons of Jupiter and Saturn. These moons could have differentiated interiors with rocky cores, ice mantles, and perhaps even thin atmospheres. The tidal heating from Planet 9 could drive geological activity on these moons, creating ice volcanoes, geysers, and possibly subsurface oceans. Imagine a moon the size of Europa orbiting Planet 9, its surface covered in fractured ice, with plumes of water vapor occasionally erupting from cracks, catching what little sunlight reaches that distance, and creating ephemeral fountains of ice crystals that fall back to the surface like cosmic snow. Such a moon would be a prime target for future astrobiology missions, a world where the combination of liquid water, chemical energy, and billions of years of stability might have allowed life to emerge. The ring system of Planet 9, if one exists, would be unlike any we have observed in our solar system. At such a great distance from the Sun, the rings would be composed primarily of water ice and other frozen volatiles, but the extremely cold temperatures might allow exotic ices we don't see in the rings of Jupiter or Saturn. Methane ice, nitrogen ice, carbon monoxide ice, all could be stable at Planet 9's distance, creating rings with unique compositions and properties. These rings might be ancient, formed billions of years ago from the destruction of moons or the capture of cometary material, or they might be young and dynamic, constantly renewed by ongoing processes. The interaction between Planet 9's rings and its moons would create complex patterns, gaps, and structures, a celestial artwork painted in ice and shadow. The captured asteroids and comets that might orbit Planet 9 as irregular satellites would provide a sampling of the outer solar system's small body population. As Planet 9 moves through its orbit, especially if it comes as close as 200 astronomical units, it would occasionally encounter and capture small bodies from the Kuiper belt and scattered disk. These captured objects would preserve information about different regions of the outer solar system, like a collection of specimens from across a vast museum. Some might be pristine relics from the solar system's formation, Others might show evidence of processing and alteration, and together they would tell the story of the outer solar system's evolution. The gravitational sphere of influence of Planet 9, the region where its gravity dominates over the Sun's, would be enormous at its distance from the Sun. This Hill sphere, as astronomers call it, could extend for millions of miles, creating a vast region where Planet 9 is the dominant gravitational force. Within this sphere, complex orbital dynamics would play out, with moons, rings, and captured objects interacting in intricate ways. Some orbits would be stable for billions of years, others might be chaotic, leading to collisions or ejections. The study of this mini-system would provide insights into gravitational dynamics that we can't easily observe elsewhere, a natural laboratory for understanding how multi-body gravitational systems evolve. The seasonal cycles on Planet 9 and its moons would be unlike anything in the inner solar system. If Planet 9's orbit is as elliptical as suspected, taking it from 200 to 700 astronomical units or more, the amount of sunlight it receives would vary dramatically over its orbital period. At closest approach, the Sun would appear as a brilliant star, perhaps bright enough to cast shadows, though still providing far less light than the full moon provides to Earth. At its most distant, the Sun would be just the brightest star among many, barely distinguishable from other bright stars in the sky. These extreme seasonal variations playing out over thousands of years would drive complex atmospheric and surface processes on Planet 9 and its moons. The magnetic field of Planet 9, if it has one, would create a vast magnetosphere extending far into space, a magnetic bubble protecting the planet and its moons from cosmic radiation and the solar wind. This magnetosphere would be unlike those of the planets we know well, shaped by the weak but persistent solar wind at enormous distances from the Sun. Charged particles trapped in Planet 9's magnetic field might create radiation belts, and interactions between the magnetosphere and any atmospheres on Planet 9's moons could produce auroras, faint glows of coloured light dancing across alien skies. These auroras would be powered not by solar storms, which would be weak at such distances, but by the planet's own magnetic and gravitational energy. The atmospheric dynamics of Planet 9 would be fascinating and complex. With a mass 5 to 10 times that of Earth, it could retain a substantial atmosphere even at the cold temperatures of the outer solar system. This atmosphere might be composed primarily of hydrogen and helium, like the giant planets, or it might have a different composition if Planet 9 formed differently or has lost its lighter gases over time. The atmosphere could have complex cloud layers, with different compounds condensing at different altitudes. Methane clouds, ammonia clouds, perhaps even more exotic compounds that only exist as gases in the inner solar system. These clouds would be driven by Planet 9's internal heat rather than solar energy, creating weather patterns unlike anything we've observed on other planets. The possibility that Planet 9 might be a captured rogue planet adds another layer of complexity to its potential moon system. If Planet 9 formed around another star and was later ejected, it might have brought some of its original moons with it, alien worlds that formed in a completely different stellar environment. These moons would carry information about their original system, their compositions and structures potentially quite different from objects that formed in our solar system. Alternatively, if Planet 9 lost its original moons during the ejection and capture process, its current moon system might be entirely captured from our solar system, a collection of Kuiper belt objects and other bodies accumulated over billions of years. the exploration of Planet 9's system, if it exists, and especially if it's closer than initially thought, might be possible within this century. At 200 astronomical units, a spacecraft using current technology would take several decades to reach Planet 9, but that's within the realm of missions we've already accomplished. Voyager 1 and 2 are still operating after more than 40 years, and New Horizons successfully explored Pluto after a 9-year journey. A mission to Planet 9 would be challenging but not impossible, and the scientific payoff would be enormous. Imagine the first close-up images of Planet 9 and its moons, revealing landscapes and phenomena we can barely imagine, answering questions we haven't even thought to ask yet. The astrobiological implications of Planet 9's moon system extend beyond the possibility of life. Even if these worlds are completely sterile, they would provide valuable comparisons to the potentially habitable moons of Jupiter and Saturn. By understanding how subsurface oceans, if they exist, behave in the extreme environment of Planet 9's system, we would gain insights into the limits of habitability and the range of conditions under which liquid water can exist. Each moon would be a data point in our understanding of planetary habitability, helping us refine our search for life elsewhere in the universe. The interaction between Planet 9 and the Kuiper Belt would be complex and ongoing. As Planet 9 moves through its orbit, it would gravitationally perturb nearby Kuiper Belt objects, sometimes capturing them as moons, sometimes flinging them into new orbits, sometimes destroying them through tidal forces if they pass too close. This ongoing process would make Planet 9's system dynamic and ever-changing on geological timescales. New moons might be captured while old ones are lost. Rings might be renewed by the destruction of small moons, and the entire system would evolve in response to these interactions. It's a reminder that even in the cold, slow outer solar system, change is constant and evolution never stops. The cultural impact of discovering Planet 9's moon system would be profound. Each new moon would need a name, probably drawn from mythology like the moons of other planets. These names would enter our language and consciousness, becoming part of humanity's expanded cosmic geography. Children would learn about Planet 9's moons in school, science fiction writers would set stories there, and future generations might even visit them. The discovery would expand our conception of our solar system from a collection of planets to a collection of planetary systems, each with its own complex environments and possibilities. Should Planet 9 exist closer than predicted, perhaps swinging within 200 astronomical units of the Sun, at its nearest approach rather than maintaining the vast distance initially calculated, it transforms our understanding of planetary formation and migration in profound yet gentle ways. This discovery would not overturn our basic understanding of how planets form, but rather add new chapters to the story, revealing that the process is even richer and more complex than we imagined. The existence of a massive planet maintaining a stable orbit in a region we thought too disturbed by the gravitational influences of Neptune and the other giants would suggest that massive planets can find stability in unexpected places, that the architecture of planetary systems is more flexible and varied than our models predicted. It would be like discovering a new room in a house you thought you knew completely, not changing the fundamental structure but expanding your understanding of what the house contains. This discovery would suggest that massive planets can maintain stable orbits in regions we thought impossible, opening new chapters in planetary science that we're only beginning to imagine. The classical view of planetary system architecture, with rocky planets close to the star and gas giants farther out, all in nearly circular orbits in the same plane, has already been challenged by the discovery of hot Jupiters, super-Earths, and other exotic exoplanets. Planet 9, especially if it's on an eccentric orbit that brings it relatively close at times, would add another piece to this puzzle, showing that even our own solar system doesn't follow the simple patterns we once expected. It would demonstrate that planetary systems are sculptured by complex processes playing out over billions of years, with planets migrating, interacting, and finding stability in configurations that might seem unlikely, but are perfectly allowed by the laws of physics. Future missions might reach this world within decades rather than centuries, bringing humanity face to face with a giant that has watched over our solar system since its birth. At 200 astronomical units, using advanced propulsion technologies currently under development, we might be able to send a spacecraft to Planet 9 in 30 to 40 years. That's within the career span of a single generation of scientists, meaning that researchers who helped discover Planet 9 might live to see the first close-up images of its surface. Compare this to the centuries it would take to reach Planet 9 if it were at 600 or 1,000 astronomical units, and the difference becomes clear. Proximity transforms Planet 9 from a distant dream to an achievable destination, from something future generations might explore to something we might explore ourselves. The philosophical implications ripple outward like waves in a cosmic pond, touching on fundamental questions about our place in the universe and the nature of discovery itself. If such a massive world can hide so close, relatively speaking, to Earth, what else might drift unnoticed in our celestial backyard? It's a humbling reminder that despite our sophisticated technology and centuries of observation, we're still in the early stages of exploring even our own solar system. The universe keeps surprising us, revealing that our maps are always incomplete, our knowledge always provisional. This isn't a failure of science, but its greatest strength, the ability to constantly revise and expand our understanding as new evidence emerges. The impact on our models of solar system formation would be substantial but not catastrophic, requiring refinements rather than revolutions. Current models suggest that the giant planets formed closer to the Sun and migrated outward, with complex gravitational interactions shaping their final orbits. Planet 9's existence would add another player to this cosmic dance, potentially explaining some puzzles in the current models. For instance, the inclination of the solar system's invariable plane relative to the Sun's equator might be explained by Planet 9's gravitational influence. The truncation of the Kuiper belt at about 48 astronomical units, rather than extending smoothly outward, might be due to Planet 9's sculpting influence over billions of years. These aren't contradictions to our models, but enrichments, adding detail and nuance to our understanding of how planetary systems evolve. The discovery of Planet 9 at a closer distance would immediately make it a prime target for detailed study, with existing and planned telescopes. At 200 astronomical units, Planet 9 would be faint but within reach of our most powerful instruments. The James Webb Space Telescope could potentially detect its infrared glow and even identify major atmospheric components. Ground-based telescopes with adaptive optics could track its motion and possibly detect large moons. The upcoming extremely large telescopes, with mirrors 30 to 40 meters across, could potentially resolve Planet 9 as a disk rather than just a point of light, revealing information about its rotation, atmospheric dynamics, and possibly even surface features if it has a visible surface beneath its atmosphere. The implications for comparative planetology would be enormous. Planet 9 would represent a type of planet common in the universe, but missing from our solar system's known inventory, a super-Earth or mini-Neptune. By studying Planet 9, we would gain insights into this class of planets that we can't get from studying exoplanets light years away. We could understand how these worlds form, how they evolve, what their atmospheres are like, whether they can have magnetic fields, and countless other questions. Planet 9 would become a Rosetta Stone for understanding the most common type of planet in the galaxy, bridging the gap between the terrestrial planets we know well and the gas giants that dominate the outer solar system. The effect on public perception and engagement with space exploration could be transformative. The discovery of a new planet in our solar system, especially one that might be reachable with robotic missions in the foreseeable future, would capture imaginations worldwide. It would be front-page news for weeks, the subject of documentaries, books, and endless speculation. Children would grow up knowing that there are 9 planets again, though Planet 9 would be nothing like the small icy Pluto we lost to reclassification. The discovery might inspire a new generation of scientists and engineers, just as the space race inspired previous generations. It would remind us that exploration and discovery are ongoing, that there are still new worlds to find and explore. The astrobiological implications, while speculative, are intriguing. While Planet 9 itself is unlikely to harbour life, being too cold and too far from the Sun, the possibility of subsurface oceans on its moons opens interesting possibilities. If Planet 9 occasionally comes within 200 astronomical units, its moons would experience varying levels of solar radiation over the course of Planet 9's orbit. This could drive complex chemistry in any subsurface oceans, potentially creating conditions where simple life might emerge. While this is highly speculative, the mere possibility expands our concept of the habitable zone and the range of environments where life might exist. Every world we discover that might harbour life, no matter how unlikely, adds to our understanding of life's potential distribution in the universe. The discovery would immediately raise questions about whether other undiscovered planets might exist in our solar system. If Planet 9 has remained hidden despite being relatively close, could there be a Planet 10 farther out? Could there be smaller planets, perhaps Earth-sized or smaller, orbiting in the darkness? The successful discovery of Planet 9 would likely trigger intensive searches for additional planets, using the techniques and technologies developed for the Planet 9 search. Our solar system might turn out to be far more populous than we currently believe, with multiple worlds awaiting discovery in the outer darkness. The impact on our understanding of exoplanetary systems would be significant. Many exoplanetary systems have planets in configurations very different from our solar system, and astronomers have wondered whether our system is unusual or whether we're simply not seeing the full picture of other systems. If Planet 9 exists, especially on an eccentric orbit, it would show that our solar system has more in common with these exotic systems than we thought. It might suggest that many exoplanetary systems have distant, massive planets that we haven't detected yet, planets that could significantly affect the dynamics and evolution of their systems. The discovery would remind us to be cautious about assuming we have a complete picture of any planetary system, including our own. The technological development spurred by confirming Planet 9's closer proximity would benefit many areas of astronomy and space exploration. Improved techniques for detecting faint, distant objects would help us find potentially hazardous asteroids, discover more Kuiper belt objects, and better map the outer solar system. Advanced propulsion technologies developed for a Planet 9 mission could be used for other deep space missions. The computational methods and AI algorithms created for the search would have applications throughout astronomy and other fields. Even the public engagement tools and citizen science platforms developed for Planet 9 would create lasting infrastructure for future discoveries. The economic implications might be surprising. While Planet 9 itself would have no immediate economic value, its discovery would likely increase funding for space exploration and astronomy. Countries and organizations would compete to send the first mission to Planet 9, potentially spurring a new space race focused on the outer solar system. The technological developments required for such missions could have spin-off benefits for Earth-based industries. The increased public interest in space might boost space tourism and commercial space ventures. While these effects would be indirect, history shows that major discoveries often have unexpected economic impacts. The discovery of Planet 9 at a closer distance would affect our understanding of the solar system's long-term stability and evolution. Numerical simulations extending billions of years into the future would need to include Planet 9, potentially revealing new insights about the solar system's ultimate fate. Will Planet 9's orbit remain stable for the remaining lifetime of the Sun? How will its gravitational influence affect the other planets over geological timescales? Could Planet 9 eventually be ejected from the solar system by a close encounter with a passing star? These questions touch on fundamental issues of celestial mechanics and the long-term evolution of planetary systems. The cultural and philosophical impact would extend beyond science into art, literature, and human consciousness. Planet 9 would enter our mythology alongside the classical planets, inspiring artists, writers, and musicians. Science fiction authors would set stories on Planet 9 and its moons, imagining what might be found there or what might have evolved in its hidden oceans. The planet would need a name, probably drawn from classical mythology, and that name would become part of human language and culture. Children would learn about Planet 9 in school, and it would become part of humanity's expanding sense of place in the cosmos. The implications for international cooperation in space exploration could be positive. A target as challenging as Planet 9, even at a closer distance, might require international collaboration to explore effectively. No single country might want to bear the full cost of a mission to Planet 9, leading to joint ventures like the International Space Station. The shared excitement of discovering and exploring a new planet could bring nations together, providing a common goal that transcends political boundaries. The scientific data from Planet 9 would belong to all humanity, expanding our collective knowledge and heritage. Chapter 9. The Eternal Dance continues. Word count, 10,000 words. And so we return to where we began, with a question that opens doors rather than closing them, a question that invites us to wonder rather than demanding immediate answers. What if Planet 9 was closer than we think? This question has carried us on a journey through the architecture of our solar system, through the patient work of astronomers scanning the darkness, through the mathematical elegance of orbital mechanics, through the deep time of solar system history, and through the implications of what such a discovery might mean for our understanding of the cosmos and our place within it. Perhaps tomorrow, or next year, or in a decade, someone will spot that faint point of light moving against the stars, confirming what mathematical whispers have suggested, revealing that our solar system has been hiding a massive ninth planet all along, a world that has been there since the beginning, patiently circling our sun in the outer darkness, waiting for us to develop the eyes to see it, and the wisdom to understand what we're seeing. Or perhaps the mystery will deepen, leading us to even more wondrous possibilities we haven't yet imagined. Science is like that, each answer revealing new questions, each discovery opening new frontiers of ignorance we didn't know existed. Maybe the orbital patterns we've observed aren't caused by a single massive planet, but by something even more interesting, multiple smaller planets, or a diffuse disk of material, or some aspect of gravity we don't yet understand. Maybe Planet 9 exists but is different from what we expect. Smaller or larger, closer or farther, alone or accompanied by a retinue of moons that would make it a mini solar system unto itself. The universe has surprised us before and will surely surprise us again, and that's part of the beauty of scientific exploration, the knowledge that no matter how much we learn, there will always be more to discover. In the vast quietude of space, where billions of years pass like gentle breaths, the search continues, and we are part of that eternal cosmic curiosity, drifting peacefully toward understanding. Every night, as darkness falls and stars emerge from the twilight, telescopes around the world turn toward the sky, their electronic eyes more sensitive than any human vision, searching for the telltale drift of a distant world. Every day, computers process vast amounts of data, algorithms sift through images, and researchers examine candidates that might, just might, be Planet 9. This search is not a sprint but a marathon, not a sudden revelation but a gradual accumulation of evidence, each observation adding a small piece to a vast cosmic puzzle. The search for Planet 9 embodies something fundamental about human nature, our refusal to accept that all the big discoveries have been made, our persistent belief that mysteries remain to be solved, that wonders await us in the darkness. We're the descendants of those who wondered what lay beyond the next hill, who weren't satisfied with the maps they inherited but insisted on exploring the blank spaces, who looked at the night sky and asked not just what those lights were but whether we could someday visit them. This curiosity, this drive to explore and understand is perhaps our species' defining characteristic, the thing that has taken us from the African savanna to the moon, and will someday take us to the stars. Consider how far we've come in our understanding of the solar system, from the ancient belief that Earth was the center of everything to our current knowledge of our place in a vast evolving cosmos. Just a few centuries ago, the solar system consisted of Earth, the Moon, the Sun, and 5 planets visible to the naked eye, all embedded in a sphere of fixed stars. Now we know of 8 major planets, dozens of dwarf planets, hundreds of moons, millions of asteroids, billions of comets, and a universe containing hundreds of billions of galaxies. Each expansion of our knowledge has made us smaller in one sense but grander in another, showing us that we're part of something far larger and more magnificent than our ancestors could have imagined. The possibility that Planet 9 might be closer than we initially thought adds a poetic dimension to this search. It suggests that sometimes what we're looking for is nearer than we expect, that our assumptions about distance and difficulty might be preventing us from seeing what's right there, waiting to be discovered. How many times in the history of science has the answer to a puzzle been simpler than expected, closer than imagined, more elegant than the complex solutions we initially proposed? Nature, we've learned, often favors simplicity and economy, and perhaps Planet Nine's orbit, while still vast by human standards, is more accessible than our first calculation suggested. The patience required for this search teaches us something valuable about the scientific process and perhaps about life itself. In our age of instant communication and immediate gratification, the search for Planet 9 reminds us that some things cannot be rushed, that some discoveries require years or decades of patient observation and analysis. The astronomers searching for Planet 9 know that they might spend their entire careers looking without finding it, that the discovery might come after they're gone, or that it might never come at all if Planet 9 doesn't exist. Yet they continue their search with dedication and enthusiasm, understanding that the journey of discovery is valuable in itself, regardless of the destination. The collaborative nature of the search represents humanity at its best, working together across borders and cultures toward a common goal. Japanese astronomers share data with American colleagues. European telescopes coordinate with South American observatories, and citizen scientists from every continent contribute their time and effort. The search for Planet 9 recognizes no national boundaries, no political divisions, no cultural barriers. It's a reminder that we're all inhabitants of the same small planet, orbiting the same star, sharing the same cosmic neighborhood, and that our greatest achievements come when we work together toward understanding our universe. The role of technology in the search highlights how our tools extend our senses and capabilities far beyond what nature gave us. Our eyes can see only a tiny fraction of the electromagnetic spectrum and can't detect objects fainter than about 6th magnitude. But with telescopes, we can see objects millions of times fainter, in wavelengths from radio to gamma rays. With computers, we can process amounts of data that would take human astronomers millions of years to examine manually. With spacecraft, we can send our robotic ambassadors to worlds we won't visit in person for generations, if ever. Technology doesn't replace human curiosity and ingenuity, but amplifies them, allowing us to explore realms that would otherwise remain forever beyond our reach. The philosophical implications of the search touch on deep questions about knowledge, reality, and our place in the universe. How do we know what we know? How can we be confident about the existence or non-existence of something we've never seen directly? What does it mean to discover something that has always been there? These questions connect astronomy to philosophy, linking the search for Planet 9 to broader inquiries about the nature of truth, evidence, and understanding. The search reminds us that science is not just about collecting facts, but about constructing coherent explanations for what we observe, building models that can predict what we haven't yet seen. The possibility of life on Planet 9's moons, however remote, expands our conception of habitability and the potential distribution of life in the universe. Every environment where liquid water might exist, where chemical energy might be available, where organic molecules might accumulate, adds to our understanding of life's possible scope. Even if Planet 9's system is completely sterile, studying it would help us understand the limits of habitability, the boundaries beyond which life as we know it cannot exist. This knowledge would be valuable not just for understanding our own solar system, but for assessing the habitability of exoplanets and their moons throughout the galaxy. The educational value of the Planet 9 search is already being realized, even before any discovery. Students around the world are learning about orbital mechanics, statistical analysis, and observational astronomy through the lens of the Planet 9 search. Teachers use it as an example of how science works, how hypotheses are formed and tested, how evidence accumulates, how theories are refined or rejected. The search provides a perfect case study of science in action, not the cleaned-up version presented in textbooks, but the messy, uncertain, exciting process of real discovery. Students who follow the search are learning not just facts about the solar system, but how those facts are discovered and verified. The potential for Planet 9 to inspire future generations cannot be overstated. Children growing up today might be the ones who first set foot on Planet 9's moons, who drill through the ice to explore subsurface oceans, who establish the first research stations in the outer solar system. The discovery of Planet 9 could be the spark that ignites a lifelong passion for science in countless young minds, leading to careers and discoveries we can't yet imagine. Every great age of exploration has inspired the next generation of explorers, and the discovery of Planet 9 could herald a new age of solar system exploration. The search also teaches us about the value of negative results in science. If extensive searches fail to find Planet 9, that's not a failure, but a valuable piece of information. It would tell us that our interpretation of the orbital patterns in the outer solar system needs revision, that perhaps multiple smaller planets or some other phenomenon is responsible. Science advances not just through confirmations, but through falsifications, not just through finding what we expect, but through not finding it and having to reconsider our assumptions. The absence of evidence in a sufficiently thorough search becomes evidence of absence, and that too advances our understanding. The cosmic perspective provided by the Planet 9 search helps us appreciate our place in the universe. We live on a small rocky planet orbiting an ordinary star in an unremarkable galaxy. Yet from this humble vantage point, we've developed the ability to detect worlds we can't see, to understand processes occurring over billions of years, to piece together the history of our solar system from subtle clues in orbital dynamics. We are the universe becoming aware of itself. Matter, organized in such a way that it can contemplate its own existence and seek to understand its origins and fate. The search for Planet 9 is part of this cosmic self-awareness, this gradual awakening of the universe to its own nature. As we contemplate the possibility that Planet 9 might be closer than we think, we're reminded of the importance of questioning our assumptions, of remaining open to possibilities that might seem unlikely but are not impossible. Science advances not just through careful observation and calculation, but through imagination and wonder, through asking "what if?" and then seeking evidence to answer that question. The greatest discoveries often come from questioning what everyone knows to be true, from looking where no one else is looking, from considering possibilities that others have dismissed. Planet 9, if it exists, has been hiding in plain sight for the entire history of human civilization, waiting for us to ask the right questions and look in the right places. The legacy of the Planet 9 search, regardless of its outcome, will be significant. It has already advanced our understanding of the outer solar system, developed new techniques for finding distant objects, engaged the public in astronomical research, and inspired countless people to think about our place in the cosmos. Whether Planet 9 is found tomorrow, in decades, or never, the search for it has enriched our species' ongoing quest to understand the universe we inhabit. It has reminded us that exploration is not finished, that discovery is ongoing, that wonders await those who seek them with patience, dedication, and open minds. And so, as you drift towards sleep tonight, perhaps you'll think about Planet 9 out there in the darkness, slowly orbiting our sun on a path that takes thousands of years to complete. Perhaps it's closer than we think, perhaps it's farther, perhaps it doesn't exist at all, and the patterns we've observed have some other explanation we haven't yet imagined. But the beauty lies not in having all the answers, but in asking the questions, in wondering about what might be out there, in being part of a species that looks up at the night sky and asks, what if? We are all part of this cosmic story, this eternal dance of discovery and wonder. And whether Planet 9 exists or not, the search for it has already taught us valuable lessons about our solar system, our universe, and ourselves. In the grand scheme of cosmic time, our search for Planet 9 is less than a heartbeat, a brief moment of curiosity in the vast expanse of space and time. But it's our moment, our question, our search, and that makes it precious and meaningful. We may be small, our lives may be brief, our planet may be just a mote of dust in the cosmic dark, but we have the capacity to wonder, to seek, to discover, and that makes us part of something magnificent. The search for Planet 9 is ultimately a search for understanding, for connection, for our place in the grand cosmic dance that has been going on for billions of years and will continue for billions more. As this contemplation draws to a close, remember that the story of Planet 9 is still being written, and you are part of that story simply by wondering about it, by considering the possibilities, by joining humanity's collective curiosity about what lies beyond the edge of the known. Perhaps someday soon, you'll wake to the news that Planet 9 has been found, that our solar system has a new member, that the mathematical whispers were correct, and a massive world has been circling our sun all along. Or perhaps the mystery will deepen, leading us in new directions we haven't yet imagined. Either way, the search continues, the questions multiply, and the wonder never ends. In the vast quietude of space, where time moves differently than it does for us, Planet 9 continues its patient orbit, whether real or imagined, closer or farther, waiting or not waiting, part of the eternal cosmic dance in which we all participate, knowingly or unknowingly, every moment of our existence. Sleep well, knowing that while you rest, telescopes continue their vigilant watch, computers continue their calculations, and somewhere in the darkness the cosmos continues its eternal dance, with or without Planet 9, but always with wonder, always with mystery, always with more to discover than we can imagine. The universe is vast, time is long, and the possibilities are infinite. What if Planet 9 was closer than we think? What if it's not? What if there's something even more wonderful waiting to be discovered? These questions don't demand immediate answers, but invite us to join the eternal human quest for understanding, a quest that continues as long as there are eyes to see, minds to wonder, and hearts brave enough to seek what lies beyond the edge of the known. The dance continues, the search goes on, and we're all part of this magnificent cosmic story. Whether we're actively searching for Planet 9 or simply wondering about it as we drift off to sleep, joining our dreams to the great dream of discovery that has driven our species from its very beginning, and will continue to drive us toward futures we can barely imagine.